The Chernobyl disaster, occurring on April 26, 1986, at the Chernobyl Nuclear Power Plant in Pripyat, Ukraine, is etched in history as one of the most catastrophic nuclear accidents. The plant, equipped with RBMK reactors known for their inherent design flaws, witnessed a catastrophic meltdown during a safety test, triggering a series of events with far-reaching consequences. The Chernobyl Nuclear Power Plant, intended to harness nuclear energy for peaceful purposes, featured the notorious RBMK reactor design. This design, characterized by a positive void coefficient and lack of a proper containment structure, contributed significantly to the disaster's severity. The disaster unfolded as a routine safety test escalated into a full-scale catastrophe. The explosion, stemming from a sudden power surge, shattered the reactor, releasing an immense amount of radioactive materials into the atmosphere. The immediate aftermath witnessed a heroic but tragic response from plant personnel, with firefighters and workers exposed to lethal doses of radiation as they desperately tried to contain the disaster. Efforts to mitigate the disaster's consequences included the evacuation of Pripyat's residents and the construction of a makeshift sarcophagus to contain the radioactive debris. Despite these measures, the human toll was devastating, with immediate casualties and a long-term impact on the health of first responders and local residents who suffered from radiation-induced illnesses. The environmental fallout was equally severe, as the explosion resulted in the widespread contamination of air, soil, and water. The effects on the surrounding flora and fauna were profound, with lasting ecological consequences that are still evident today. Internationally, the Chernobyl disaster prompted a paradigm shift in nuclear safety protocols. Countries worldwide reevaluated their nuclear energy policies, emphasizing stringent safety measures and international cooperation. The disaster served as a grim reminder of the potential consequences of nuclear accidents and the importance of transparency and information sharing. Decades after the Chernobyl disaster, the affected region remains a haunting reminder of the perils of nuclear energy. Efforts continue to monitor and mitigate the long-term environmental and health impacts, underscoring the lasting legacy of this tragic event in the annals of nuclear history. How nuclear power plants work. A comprehensive overview. Nuclear power plants generate electricity through controlled nuclear reactions, harnessing the immense energy released during fission processes. The fundamental principle behind their operation is the controlled splitting of atomic nuclei, typically uranium-235 or plutonium-239. This process releases a substantial amount of heat, which is then utilized to produce steam and drive turbines connected to generators, ultimately generating electricity. The core of a nuclear power plant houses the reactor, where nuclear fission reactions take place. Within the reactor, fuel rods containing enriched uranium or plutonium are carefully arranged to sustain a controlled chain reaction. The control rods, made of materials that absorb neutrons, are inserted or withdrawn to regulate the reaction's intensity, ensuring a steady and manageable release of energy. As fission reactions occur, the released heat is transferred to a coolant circulating through the reactor core. Water or gas commonly serves as the coolant, absorbing the heat and preventing the reactor from overheating. The heated coolant then travels to a heat exchanger, where it transfers its thermal energy to a secondary system without coming into direct contact with the reactor. The secondary system typically uses water to create steam by exposing it to the heated coolant. This steam, under high pressure, is directed towards turbines, causing them to rotate. The turbine's mechanical energy is then converted into electricity by a generator. This process is akin to traditional power plants, albeit with the key difference of the heat source being nuclear fission rather than the combustion of fossil fuels. Safety measures play a crucial role in nuclear power plants. Control systems continuously monitor reactor conditions, and various safety mechanisms, including emergency cooling systems and backup power supplies, are in place to prevent overheating and ensure a safe shutdown in case of emergencies. The spent nuclear fuel, containing radioactive isotopes and byproducts, is carefully managed. It is often stored in cooling pools or dry casks on site, and long-term disposal strategies are being researched and implemented to address the issue of nuclear waste. While nuclear power provides a significant source of low-carbon electricity, concerns about safety, radioactive waste, and potential for accidents have led to ongoing debates surrounding its use. Advancements in technology and increased focus on safety standards continue to shape the future of nuclear energy, aiming for a balance between its potential benefits and the imperative to address its associated challenges. The human impact of the Chernobyl disaster, a comprehensive examination. The Chernobyl disaster of 1986 had profound and lasting effects on the lives of individuals in the affected region and beyond. The immediate aftermath witnessed a tragic toll on the brave firefighters and plant workers who responded to the emergency. Many of them suffered acute radiation sickness, leading to immediate casualties and long-term health consequences. The high doses of radiation exposure resulted in severe burns, nausea, and, in some cases, fatalities. The heroic efforts of these first responders, often working in perilous conditions, underscored the human sacrifice in the face of a nuclear catastrophe. In the years following the disaster, the residents of Pripyat and surrounding areas faced significant health challenges. The evacuation of the city and nearby settlements was a critical measure to limit radiation exposure. However, the displaced population endured the psychological trauma of leaving their homes, coupled with the uncertainty of their future health. Long-term health effects, including an increased incidence of thyroid cancers, leukemia, and other radiation-related illnesses, continued to manifest over time. The impact on maternal and child health was particularly notable. Pregnant women exposed to radiation faced an elevated risk of delivering infants with birth defects and developmental abnormalities. The region experienced a surge in infant mortality rates and a heightened prevalence of childhood cancers. These effects highlighted the intergenerational consequences of nuclear disasters, as the genetic damage caused by radiation exposure persisted through subsequent generations. The psychological toll on the affected communities was substantial. The fear of radiation and its invisible, insidious effects led to heightened anxiety and stress among the residents. Stigmatization and discrimination against those from the affected areas further exacerbated the psychological burden. Many survivors faced not only physical health challenges but also the societal impact of being associated with a nuclear disaster. The Chernobyl disaster also prompted international efforts to study its human health effects comprehensively. Collaborative initiatives, such as the Chernobyl Forum, sought to assess and address the long-term consequences on the exposed populations. Research findings have contributed to a better understanding of radiation's impact on human health, influencing future safety protocols and disaster preparedness measures. Decades later, the human impact of the Chernobyl disaster continues to be studied, emphasizing the importance of learning from such tragedies to minimize the consequences of future nuclear incidents. The survivors' stories serve as a poignant reminder of the profound, far-reaching effects that nuclear disasters can have on the lives and well-being of individuals and communities. Nuclear energy engineering. Nuclear energy engineering is a specialized field that focuses on the design, development, and operation of nuclear power systems. Professionals in this field play a crucial role in harnessing the immense energy released during nuclear reactions to generate electricity in a safe and efficient manner. Nuclear engineers work on various aspects of nuclear power plants, including reactor design, fuel management, and safety protocols. One of the key responsibilities of nuclear energy engineers is the design and optimization of nuclear reactors. This involves selecting appropriate reactor types, such as pressurized water reactors, PWRs, or boiling water reactors, BWRs, and developing strategies to enhance their efficiency and safety. Engineers also work on innovations in reactor technology, exploring advanced designs that address concerns such as waste disposal and proliferation risks. Fuel management is another critical aspect of nuclear energy engineering. Nuclear engineers are involved in the development and utilization of nuclear fuels, such as enriched uranium or mixed oxide (MOX) fuel. They work to ensure the sustainability of fuel resources, maximize energy output, and minimize the production of nuclear waste. Additionally, engineers address the challenges of spent fuel management and the safe storage or disposal of radioactive byproducts. Safety is paramount in the field of nuclear energy engineering. Engineers develop and implement stringent safety measures to prevent accidents, manage emergencies, and protect both plant personnel and the surrounding environment. This includes the design of advanced control systems, emergency shutdown procedures, and the continuous improvement of safety standards. Nuclear energy engineers also contribute to risk assessments and the development of protocols to mitigate the potential environmental and health impacts of nuclear power generation. Overall, the field of nuclear energy engineering plays a pivotal role in advancing sustainable and secure solutions for meeting the world's growing energy demands.